Recording in progress.
Welcome everyone. Today we speak about rings. Rings is a empty set like R and two binary operation plus and dot, such that R with plus is an abelian group and R with dot is a semigroup. It means it is associative and closed. Also, we have distributive law. That means for any A, B, C in R, we have A dot B plus C must be equal to A dot B plus A dot C. Then we called the triple R plus dot a ring. This ring is called commutative if for any AB in R, AB, I means A dot B equal to B dot A. For any AB in R, then R is commutative. R is commutative. We now give some examples. Before that, we say that R is a ring with unity if R has the unit 1. If 1 contained in R, then we say that R is a ring with unity, or R is a ring with identity. Sometimes we say that R is a unitary ring. A unitary ring. That means we have the identity 1. Now we give some examples. About rings. Of course, Z, the set of integers, Q, the field of rationals, and the field of real numbers, and the field of complex numbers are rings, and commutative rings with identity. Also, we have the integers modulo n, Zn, with plus n and dot n is a ring also. So we have the isomorphisms Zn isomorphic to Z over nz. So these two sets are the same. Also, we have when we adjoin a ring with a variable or indeterminate x, we say that the ring of polynomials, we adjoin R with indeterminate x, say a variable, which is the set of all polynomials in X. That is A0 plus A1 x plus up to AN x to power n, where AI in the ring R. This is called polynomial ring. Polynomial ring which is contains the ring, the set R adjoint to X. So as an examples for polynomial rings, we have Z of I, which is called Gaussian integer ring. We know I is a root for a polynomial x squared plus 1 equal to 0. So Z of I is a polynomial ring, but the polynomials written as A0 plus A1 I, because if we write the next term, which is A2 I square, this I square is equal to minus 1, and minus 1 is an integer, so it belongs to Z as a first component. We cannot write this A0 two times, so it's sufficient to I to power 1, because I is a root of a polynomial of degree 2. So the polynomials in Z of I must be polynomials of degree 1 degree less than the polynomial P of X, say. Of course, A0 and A1 are in Z. So, for example, if we have x such that x to power 3 equal to 0, then the polynomial ring R of x must be written as A0 plus A1 x plus A2 x square, but we don't, it don't need to write x to power 3 because it is a 0 term. So it's sufficient to write up to x to power 2 and AI are in R. So this polynomials ring, we can write like this R of x divided by the ideal x to power 3. This it means that in the polynomial ring R of x, we have x to power 3 is 0. So the elements are as this such polynomial: A0 plus A1 x plus A2 x square. We have another examples, like say Z of pi, which is not algebraic number. It's a non-algebraic number or transcendental number. So it's the set of all polynomials like A0 plus A1 pi plus up to AN pi to power n, because pi is not a root of any polynomials over Z. AI in Z. Also, we have Z of, say, the cube root of 2. Cube root of 2 is a root of the polynomial x to power 3 minus 2 equal to 0. This polynomial is of degree 3. So the polynomials in Z of cube square of 2 must be polynomials like a0 plus a1 cube root of 2 plus a2 cube root of 2 square, but we don't write cube root of 2 to power 3 because it's a root of a polynomial of degree 3. So the polynomials in polynomial ring Z of cube root of 2 must be of degree less than 3 by 1. That is polynomials of degree 2. So AI in Z. Here, the cube root of 2 is an algebraic number. That is, it's a root. It is a root of a polynomial like x cube minus 2 equal to 0. But in above example, z of pi is not algebraic number because pi is not a root of any polynomial over z. Pi is non-algebraic number. So we deal with non-algebraic numbers as an indeterminate, like x. So z of pi is the same as we say that z of x. X is indeterminate over z, and pi is 2, is indeterminate over z. So they are the same. We have another example. Let we have an empty set S. We denote by f of S to be the set of all maps F from S to the set of real numbers. This set F of S is a ring. With the binary operations plus and dot defined as for any fg in F of S, we have f plus g of x equal to f of x plus g of x. And for dot, we have f dot g of x equal to f of x multiplied by g of x. This is another example about ring. Another example, if you have the power set of S is an empty set, the power set P of S equipped by the two binary operations, symmetric difference and intersection. This is also another example of a ring Of course, this ring has identity, which is x, and it is zero element is phi. Also, for any element a in the power set of S, that means A is a subset of S. We have A square equal to A. It means A square A intersection A is equal to A for any element A in the power set F of S, P of S, sorry. For polynomial rings, as we said, R of X, we have the invertible elements, only the invertible elements of R. For example, X has no inverse. We can adjoin sometimes a ring R with the inverse of X, or with X and the inverse of X. Let's clarify R. When we say that R of X inverse, it's the same as R of X, but we instead of any X in the polynomial, we write X inverse. So R of X inverse is the set of all polynomials A0 plus A1 X inverse to power 1 plus A2 X inverse to power 2 up to AN X inverse to power N and AI in R. That means A0 plus A1 X inverse plus A2 X to power minus 2 up to AN X to power minus N, and AI are elements of the ring R. So for any ring R, we can adjoin X or X inverse or X and X inverse together, like R of X comma X inverse is equal to the polynomial rings. Polynomials like A0 plus A1 X up to AN X to power N plus this is for X, and the same for X inverse. Say B0 plus B1 X inverse plus Bm X to power minus M. So we add B0 and A0 to be one element in R. We can write this polynomials as a summation AI X to power I from negative M to N, where AI in R and M are positive integers. This ring when we adjoint a ring R with X and X inverse, is called Lorent polynomial ring. Lorent polynomial ring. For example, you can say z of square root of 2 and 1 over square root of 2 is the set of polynomials written as a summation ai square root of 2 to power I from minus m to n, where ai are integers. So in the set of polynomials with a finite term of negative powers, for example, we have maybe 1 over square root to power 1 plus 3 square root of 2 plus 7 is an element of z of square root of 2 and 1 over square root of 2. Of course, as we write before here, z of square root of 2 or cube root of 2, since square root of 2 is a root of a polynomial of degree 2, that means square root of 2 is a root for a polynomial like x squared minus 2 equal to 0. This polynomial is of degree 2. So the polynomials in the polynomial ring must be of degree 1, 1 degree less than the polynomial x squared minus 2. So this summation must be start from minus 1 to minus 1 to 1. Minus 1 to 1. That means we have square root of 2 to power 0 or to power 1 or to power minus 1. Of course, with constants, integer numbers. We can say we have z of, for example, z of 1 to over 8 contains z of 1 over 4, which also contain z of 1 over 2, and this one contain z of, say, 1 over 2 to power 0, because 1 over 8 is 2 to power minus 3, and 1 over 4 is 2 to power minus 2, and 1 over 2 is 2 to power minus 1. Here you can say that 2 to power 0. 2 to power 0 is the same as we say 1, and z of 1 is the same z, and this z contain 2z, the set of even integers. Also, this one contain 4z, and this one contain 8z, and so on. So this one, as we say, the even integers like z of 2 to the power 1, not as adjoint z with 2, but it is the multiple of 2, and 4z are the integers multiple of 4, and az are the integers of multiple 8, like 8r, 4r in z. We have also power ring, power series ring, power series ring, written as r of x into brackets is the set of all power series like ai x to power I from 0 to infinity, and ai in the ring R. The set of all such power series is a ring with the addition and multiplication of series. If we adjoint also x inverse, we get R of x and x inverse is the set of all Lorent series AIXI I from minus m to infinity. That is a power series from 0 to infinity with addition to some negative terms. Of course, AI are in R. This ring is called Lorent series ring because their elements are Lorent series. As we will study in complex analysis, so we call it Lorent series ring. Now we give some examples of non-commutative ring, especially matrices. Non-commutative rings. For example, Mn of R. Let R be a ring, then Mn of R is the set of all M by N matrices. n by n with entries in R. That means M, I, J are elements of the ring R. Also, we have a quaternion ring H, which is the set of all elements like A plus B I plus C J plus D K, where A, B, C, D are real numbers. This ring is called quaternion ring. Of course, every non-zero element in this ring have inverse. For example, if we take alpha to be equal to A plus BI plus CJ plus DK, then its inverse is I minus BI minus CJ minus DK over A square plus B square plus C square plus D square. So we can say this ring is a division ring. That means H have identity element 1, which is equal to 1 plus 0i plus 0j plus 0k. And every non-zero element has inverse, as I said. So it's a division ring. Division ring, it means it is a field, but non-commutative, a non-commutative field. As we say that in the definition of ring, if R with dot not semigroup is an abelian group, then the ring R is called a field. But if R with dot is semigroup, it's called a ring, just a ring. Also, we have the implication, the real set of real numbers is a subset of the set of complex numbers, and this one is a subset of the quaternion ring H, because here I, J, and K with 1 are the vectors in the four Euclidean vector space. That means we have I square and J square and K square equal to 1, and I dot J equal to K and equal to minus J dot I, and j dot k equal to I and equal to minus k dot j. By this circle, we can define the dot we go in the direction of in the direction of clockwise. So I dot j is k and j dot k is I, and k dot I is j, which is equal to minus I dot k. By these relations, the quaternion ring is defined. As we said before, if alpha is algebraic number, that means alpha is a root of some polynomial, then we have q of alpha is a field and written as q of alpha is a field. But if alpha is non-algebraic or transcendental number, then q of alpha is not a field. For example, q of pi is not a field because pi has no inverse. Otherwise, if we said pi has inverse, that means if pi inverse is exist, then pi inverse must be written as a polynomial of pi, say g of pi. Now we multiply each side by pi. We have pi dot pi inverse equal to pi g of pi. And since pi inverse is equal to 1, this one, so we have 1 equal to pi g of pi. Hence, pi is a root of the polynomial f of x, which is equal to x g of x minus 1 above, which is mentioned above, and this is a contradiction. Because pi is non-algebraic, is not a root of any polynomials. Hence, q of pi is not a field. We know if we have two rings, say R and S, we define direct product of R and S as R direct product with S is the set of all ordered pair RS, R in R, and S in S. This set is a ring with addition and multiplication of ordered pairs like R square and etc. That means if we have RS with AB, if we add these two elements, we write R plus A and S plus B. So we make the addition component twice. And also for the multiplication, RS dot AB is equal to R multiplied by A and S multiplied by B. So in these two binary operations, we have RS is a ring. This ring in any situation cannot be a field, even if R and S are fields. Then R cross S, the direct product of R and S, is not a field. Because we have 1, 0 multiplied by 0, 1, which is 0. But no one of these two elements is 0. Because in field, if A dot be equal to 0, must A be 0 or B is 0. This is a condition in fields. But here we have two non-zero elements whose product is 0. So the direct product of any two rings cannot be a field. Now, as in group theory, every finite group G can be written as the direct sum of Z sub Ni, where I from 1 to K that means G is the direct sum or direct product of Z and I. And since each Z and I is a ring with plus and dot of Ni, so we can regard this direct sum or direct product of Z and I as a direct product of rings. So we can say every finite group can make as a ring, can be met as a ring. Now, like group theory, in group we have subgroup. In vector space we have subspace. Even in module we have submodule. Here in ring we have subrings. Subring, an empty subset of a ring R is called subring if S forms a ring, or we can give two conditions to S to be a subring of R, which is for each A be in S, A minus B must be in S, and A multiplied by B, A dot B must be in S. That means S is closed in plus and dot. Of course, the intersection of any two subring is a subring. Even the intersection of any family of subrings of a ring is a subring of that ring. But the sum of two subrings not necessarily be a subring, and the product of two subrings may be not a subring. For example, if we take z of x, y, the polynomial ring in two variables, x, y, and we take two subring, z of x and z of y as subring of z of x, y. The sum of such two subrings and their product is not a subring. That means z of x plus z of y, or z of x multiplied by z of y, are not subrings. Of z of x, y. You can check it. Also, we have ideals in ring. Ideals. An empty set I of a ring R is called an ideal if we have two conditions. For any A B in I, we have I minus B in I. Also, for each A in I and for each R in the ring R, we have RA, AR in I. For examples, in the rings of integers Z, the ideals are NZ, like 2Z, 3Z, 4Z, and so on. We have many types of ideals, like prime ideals, maximal ideal, nil ideal, nilpotent ideals, idempotent ideal, and we have operations on ideals like the sum of two ideals, intersection of two ideals, and of course the union of two ideals need not be an ideal. For example, 2z union 3z is not an ideal. In another video, I will speak on the types of ideals, but here we go to the characteristic of the ring. Another term in ring theory is the characteristic. Which is the large non-negative integer n such that n dot 1 equal to 0. The largest non-negative integer n such that n multiplied by 1 equal to 0. For examples, in Zn, the ring of integers modulo n, their characteristic is n. So the characteristic of Z2 is 2, and Z3 is 3, and Z5 is 5, and so on. Also the characteristic of Q and the characteristic of the set of real numbers and the characteristic of the field of complex numbers is 0. Also the characteristic of Z over nz is n. Boolean rings is an example of ring. Boolean, which has many applications in computer science. Boolean ring is a ring R such that for each A in R, A square equal to A. This ring with this property is called Boolean ring, and this ring always have characteristic equal to 2. Of course, the converse is not true, since we have the ring Z2 of X, Z2 of X, which contains the element 0, 1, X, and 1 plus X. Because it is the set of polynomials with coefficients in Z2 which are 0, 1. So we have this elements. Of course, we have 1 plus x square, and maybe 1 plus x square, and x plus x square and x square plus x cube, and so on. So of course this ring has characteristic 2 because it depends on Z2, which has characteristic 2, but we have x as an element in Z2 of x such that x square not equal to x. So this ring has characteristic 0, of course, characteristic 2, but it is not Boolean ring. In next video, we will speak about the types of ideals and Jacobson radical and near radical of a ring, and so on. Now we finish. Goodbye.